Hi, welcome. I'm Jordan Zink. This is my presentation on Newton's three laws. We will be diving deep into them and giving some real world examples. So a few topics we're going to cover is a little history about Isaac Newton and some of his other contributions other than the three laws, and then of course the three laws. I apologize if I'm nasally. I'm just not getting over a cold. Okay, but diving in here to young Isaac Newton and education. Isaac Newton was born in 1643 in Woolsthorpe, England. He was the son of a farmer, but his father actually died 3 months before he was born. Um, he attended King's School in Grantham before enrolling in Cambridge University in 1661. It's worthy to note that 1600s had a lot of plague, and the Great Plague of London ended up um, forcing him to leave Cambridge and going back to the farm where he theorized calculus, light, and color. And that's where is rumored where the apple fell, where he got his epiphany. So moving on to his other contributions, Newton began working with refraction and light, leading to the development of the first telescope. He figured out that white light was a composite of all colors and discovered light was composed of particles and not waves. He was also the founder of calculus. The reason why I put parentheses there is because there was some, you could say, drama between him and this German guy, Gottfried Leibniz, who also was theorizing calculus, and researchers figured out that they were just doing it on their own accord, which I think is interesting. He also theorized elliptical paths of celestial bodies, which led to the publishing of his Principia Mathematica, one of the books he published, and then, of course, he determined the law of gravity and the three laws of motion. Now, looking into those briefly here, the first law states that an object in motion will stay in motion, as will an object at rest stay at rest, unless an external force acts on it. The second law states that the force of an object is equal to its mass multiplied by its acceleration. That's F equals ma. The third law states that for every action, there is an equal and opposite reaction. Basically, F equals negative F. Okay, diving deep into Newton's first law here. Say you have a ball and you're in outer space and you throw it. That ball's going to have a consistent velocity and direction unless it hits something in space or whatever. The point is, if it's in motion, it's going to continue in that motion unless gravity or whatever acts onto it. The flip side of that is a book resting on a counter is in equilibrium with the counter. So essentially, it's not going anywhere. In my example here, with my fridge, um, is exerting a force down as the floor is exerting that force right back up, and it's staying at rest, and it will stay at rest until a force has is greater than the static friction acting on the object, and that's the problem we're about to get into here. So I made a little problem here with the fridge. So we have some units, and we know that mg is a downward force, and that's 490. We know that n equals mg, so n equals 490. And notice I have the directions here because our forces have directions. Okay, so we want to know how much force we exert this way to overcome the static friction that is exerting the force this way. And to get the static friction, we have our mu, our coefficient, and we're going to multiply that by our normal force and get 147 newtons. And of course, that's going in the left direction. And we're just showing here that this is what it takes to just get the fridge moving. So this is net force, and of course, just to get the fridge moving, it has to be at least equal to the static friction, which is 147. So it takes 147 newtons to move the fridge. Going into Newton's second law is F equals ma, and we're going to look at my drawing of a car here, and it is going forward, and it's going forward by 20,000 newtons. So the muffler is shooting at 20,000 newtons worth of force, and that is what's propelling it forward. It weighs 850 kilograms if we want to find the acceleration. So we're going to use this one here. And that gives us 23.53 meters per second per second. So that'll be a fast car. Okay, going into Newton's third law here. We have another outer space problem, and I like outer space because there's no variables, so it's easy to explain things. And the first law is always prevalent. Um, so the astronaut is away from a shuttle, and he throws a rock, and so he's exerting the force on the rock that way, but that force is actually exerting a little force back on him. And since there's nothing to stop him moving in outer space, he's going to continue that way and float back to his shuttle. And he did that through Newton's third law. And we're going to look at another example here. Is a little drawing I did of a guy playing tug of war with the wall. So this is the force the force of the applied force plus the force of the reaction force of the wall, and you see how that equals, because it's going in the different direction. They're equal to each other, because if he's pulling 200 newtons that way, the wall's pulling 200 newtons the other way. Okay, so I really enjoy golf, so I thought it was fun to do some real-world golf problems. And so golf uses the three laws in conjunction with one another all the time. So in this picture right here, you see the ball is at equilibrium with the tee, and excuse me, I have to get my cat. You can say hi. Sorry. The first law, the ball is at equilibrium with the tee, and it's not going to move anywhere until the club hits the tee, unless an external force acts on it. So the second law is the movement of that club coming down on the tee, and that's the force that it's generating. And then the third law is when it comes into contact with the ball, the force of that club acting on that ball is going to cause that ball to launch. But if you play golf, you know that when you hit the tee, that ball is exerting a force back onto the club as well, and you can feel that through your club and possibly through your arms a little bit. So here was a scenario that I was in where I was 3 meters from the hole, and I need so we're not gonna watch that just yet. And I wanted to know the force required to get there. So here's my problem. So I have the weight of the golf ball, 45 grams. It takes 2.3 seconds to get there, and I know it's 3 meters. I first have to calculate the velocity, and then I plug it into this equation here, which gives me my force of 12.675. Alright, now let's check it out. Aced. Sweet. Okay, we're going to go to our second problem here, and this is a range shot. Same equation, but now we're going to find the distance, because I'm going to be using a 6-iron here. It's going to go a lot further. So the weight is the same, but the force of my swing has changed, because it's going to be a full swing with an iron, and that's going to be a larger force. And then the velocity of the ball coming off the tee is 150 meters per second. Okay, so we plug and chug these numbers, and we're going to find the distance is about 180 meters, which makes sense for a 6-iron. Let's take a look. Alright, nice. So the bonus slide, this is my favorite golfer. He's a professional golfer and majored in physics. He's a physicist, and he brought physics to the game of golf to the point that nobody could even imagine. So in golf, when you have a 9-iron, it's short, and when you have a 5-iron, it's long, and it generates more power. Well, this guy's club is all the same. It weighs all the same. The only difference is the angle in the club, where a higher club is going to make it have more loft, more height, and the other club's going to be in the lower your club, the more distance it's going to be going. So he won first place at 2020 U.S. Open, and not only did he win first place, but he won by 6 strokes, which is incredible. And that's all I have. Thank you for watching.